In between the white layers, which are quite clear, represent the winter snowfall. So what we have here is a sort of a glaciological tree ring system.
Right.
So what we have summer, winter, summer, summer, winter, summer, and on we go.
And about how old a sample would you say this is?
This is at 2,300 meters. This is probably somewhere in the range of 50,000 years.
Okay.
Dr. Peter Grudis from the University of Washington explains how the oxygen isotope data he analyzes gives information on temperature.
From the 1 meter section to take 1 ounce sample back home to the laboratory, they will analyze the O18, O16, the oxygen isotope ratio in the mass spectrometer. And from this mass spectrometer isotope ratio, we can make inferences about climate. Here's an example of the results we got last year. You see the isotope values varying between lower and higher values with a difference of about 5 per mil. What it shows us, the high values correspond to warmer phases of the last glacial period, and the low values correspond to cold phases. The reason you can get climate and temperature from isotopes is that the heavy isotopes, so 18, evaporate a little bit less readily and fall out more easily. And so if the water vapor, which forms at mid to low latitudes, is transported to the Greenland ice cap, and the cold conditions, more of the heavy isotopes are lost. So you get low isotope values, and the warm conditions, less is lost, so you get more of the heavy isotopes. And this way we get a record of climate in the past. The variations that you see here correspond to about 5 per mil, which is about 7 or 8 degrees Celsius. And this way we can get a record of temperature fluctuations in the past from the ice core.
Dr. Richard Alley from the University of Pennsylvania describes what he has found from his analysis from the ice core layer.
The beauty of the GISP core is this annual layering, or one of the beauties of it, is that you really can do summer, winter, summer, winter. And any number of us have worked on pulling that record out. The next thing, though, is that when you take that record out of the last 10,000 years and run into the Ice Age, there's huge changes in accumulation right at the same time as huge changes in temperature. They correlate very well. But the interesting thing there is that the accumulation changes more than it could just from warm air holding more moisture. So it can't be thermodynamics. It's not this warm air has got more in it. What it has to be is something about the storminess. Either the cold periods don't have any storms, or the cold periods have storms that are going somewhere else, but they're not going to Greenland. Correct. When it gets cold, the storms go away from Greenland. They're there somewhere. They're stirring up dust, they're stirring up sea salt, but they're not bringing moisture to Greenland. When it gets warm, they come back to Greenland. So we're starting to pull together this picture. What does a cold period look like? And the cold period clearly looks like not much snow. It clearly looks cold. It clearly looks great windiness, because there's 3 times more sea salt in the younger Dryas atmosphere over Greenland than there is in the warm atmosphere just afterwards. The Ice Age, the real Ice Age conditions is even bigger changes. So there's lots of wind moving somewhere, but it's not moving over Greenland. It's taking the storms and the water and taking them to Spain or somewhere, but not to Greenland. So we're starting through all of the work, what we're doing and what everybody else is, we're starting to take a clear picture of how fast and in what fashion these changes occur and what they affect, how far out. The eventual hope is to understand them well enough to know whether they could happen again.
A part of the core is melted so that it can be properly analyzed in the chemistry lab.
This whole thing is heated, and it melts down around it, sinks down. The center part is funneled into the center and into our bottle.
The samples are run through an ion chromatograph to measure chemical composition.
Okay, here we go. This is our ion chromatograph that we use to measure the cations and anions in the ice core. On this instrument we measure for anions, we measure chloride, sulfate, nitrate. For cations, we measure sodium, ammonium, potassium, calcium, and magnesium.
At the end of the core processing line, the remaining pieces of core are carefully packaged for return to the U.S. for future analysis.
Which is what we call the packing area, where the 2-meter piece of ice core, after the ECM is done on it and the stratigraphy is recorded, is cut into 1-meter sections and packaged into silver tubes, into a plastic liner, and then into silver tubes, and recorded and sent off to the ice core repository in Denver.
It's now near the end of June 1993, the 5th summer of the project, and the goal, bedrock, is very close. The drill is at 3,040 meters, and anticipation runs high. The first sign comes on June 23rd. There's a small, distinct pebble embedded in the ice. Then early the next morning, the core turns to silty ice. And another 13 meters and it's bedrock and success. It's the first time that central reaches of an ice sheet has been penetrated right through to the bottom. The world's longest core, 3,054.3 meters, 10,021 feet. Such an accomplishment calls for a celebration for everyone at the camp.
Okay.
You should have a hand on the champagne.
How about a dual shave on the champagne? Yahoo! You don't have any glasses?
One of the scientists, Mike Savage, has a ham radio rig and sends out a message to the world.
K9JJR and the net from Ocean X-ray stroke N7PQO, located on the summit of Greenland. And I'm happy to announce that today our drilling team reached bedrock. I have a message prepared by our chief scientist that I'd like to read now. As follows. On 1 July 1993, at 2:48 p.m. local, the U.S. Greenland Ice Sheet Project, GISP-2, located in central Greenland, 72 degrees north, 38 degrees west, elevation 3,208 meters, struck rock. This completes the longest environmental record, 3053.51 meters, representing approximately 250,000 years of the Earth's history.
Our European colleagues and neighbors from GRIP, the Greenland Ice Core Project, 18 miles away, have also drilled a parallel core. The two records together show close agreement through most of the core length. Another important part of this National Science Foundation-funded Greenland project took place at a remote camp 18 miles from GISP-2, where the atmospheric sample station gathered air and snow samples in what is known as one of the most remote areas of the Arctic. The air gathering pumps at ATM are operated entirely by pollution-free solar panels, rated at 6 kilowatts. Samples of windborne contaminants are taken for researchers all over the world. Whenever the wind direction changes, bringing pollution from the GISP-2 generators, the whole system shuts down automatically. With the ice coring completion, camp manager Jay Klink arranges for the LC-130s to fly the ice core samples and the camp personnel back to the United States.
It's now 1994. Approximately 1 year ago, we finished drilling. And although we still have a considerable amount of analysis and interpretation that we need to do before we truly understand the record that we've recovered. A great number of very exciting papers have already appeared in press, and many more are in the process of being prepared right now. What I'd like to be able to do is share some of those ideas with you right now. In the early stages of our program, we were particularly interested in investigating a portion of the paleo record called the Younger Dryas. This is a rapid return to cold conditions immediately following the collapse of the large great ice sheets that covered North America and Europe, a time when there was still sufficient ice left for cold conditions to be felt again. We've been able, with the GISP-2 record, to document in quite a great bit of detail the Younger Dryas. Its rapid onset in probably less than a decade, its rapid decline in probably less than a decade, a series of rather cyclical events that make up the Younger Dryas, which have parallels in moraine events, in particular in Scandinavia, and also the very, very dramatic changes in accumulation, temperature, dust content, and gas content that characterize the Younger Dryas. One of our tasks when we undertook the GISP-2 program was to determine whether or not the rapid climate change called Dansgaard-Oeschger events actually existed in the Greenland record. They'd been observed before in a record from South Greenland, but there was some question as to whether or not they were flow deformations within the ice sheet or whether they were true climatic events. Without a doubt, because of the presence of two cores at the summit site, the European core and our core, we've been able to substantiate the presence of these so-called Dansgaard-Oeschger rapid climate change events, demonstrating that they not only exist, but the onset and decline of these events, similar to the Younger Dryas, occurred very, very rapidly within a decade or a couple of decades, and that there is a great deal of structure that occurs even within these events, a great deal of superimposed, or a great number of superimposed rapid climate change events. Well, the debate about what these rapid climate change events actually represent will probably continue for a while. It seems clear now that a large part of the activity that we observe in these events can be represented by dramatic changes in the distribution of circulation that enters Greenland. This is probably the only way in which we can account for changes in climate which would have occurred over a decade or less. When you have records of the quality of the GISP-2 record available to you, and by quality I mean the resolution, the continuity of the record, the number of variables measured, there are a tremendous number of things that we can potentially learn about climate change. One of the things which we might very well ask ourselves first is that, is there any order in this record? Is there any order in the way nature appears to behave? The preliminary answer to this question is absolutely yes. We can see very, very clear signatures of the relationship between the Earth and the Sun and the changes in the amount of insulation received by the Earth from the Sun, forced into our record as they are into the marine records. We can see evidence of volcanic activity. We can see evidence of perhaps even solar activity. Many of these provide us with very, very regular, very periodic signals that pervade throughout the entire record. It is the presence of these periodic signals which, if we can truly understand, will without a doubt provide us a great deal of information about not only how climate functions, but how it may very well function in the future, and what human activity has done to alter such cycles.
For the last millennium, the effects of climate on humans has been a subject of great wonder. Perhaps we're coming closer to understanding climate changes through projects like GISP-2.